Your pages are so much easier when there's no application. I love that. Your pages are so much easier when there's things.
All right. So going over this one, there are a lot of different variations they could ask of this question as. So if you take an element like zirconium, it can be any element off the periodic table. So this particular one is asking us about unpaired electrons. In order to visualize unpaired electrons, you kind of, unless you can just see it, you kind of have to recognize that in the 4D orbital, there's going to be 2 electrons, so they're going to be on separate blanks. All right, so that gives us the 2 unpaired. Now realize these 2 unpaired are actually in our, 4D. It's not our outermost shell. It's actually an inner shell that has the unpaired. All right, now another way that they can ask this question is about core electrons versus valence electrons. So valence is based on the outermost shell. So the outermost shell in this one happens to be the 5th shell or the 5th quantum level. So the 2 electrons that are in the valence shell are coming from these 2 electrons. That's the ones that would be gained or lost in an ionic interaction. All right. Now, where do I get the number of 40 total electrons for this? If we're assuming it's a neutral atom, the atomic number and the electrons are equal. All right. So that's where that comes from. Now, so the other 2 things, and these 238s are coming from different places as well. So when I say 38 core electrons, I'm talking about there's 38 electrons in quantum levels 1 through 4, because quantum level 5 is my outer shell. That's my valence. But when I say there's 38 paired, that's going to be, the 5s, the 4p, the 3d, the 4s, and everything below that. So just recognize that when we're talking about paired and unpaired, that can have different numbers than valence and all of that. This one just happened to have some correlations between things. This is a Hund's rule example, because remember, Hund's rule says that our last place that we're filling has to give a maximum of unpaired. So that's where we're looking at on that. So if I was looking at iron instead, I would have had 4 unpaired electrons on this one because iron is 6 places into the D, so it would have 4 unpaired. All right, so I just wanted to kind of go through that and give you an example question of something you might see on the test or a way that they would ask it. But remember, they can ask 4 or 5 things from that same scenario. So, all right. So today we are moving forward with Chapter 9. For the most part, we're going to be finishing up the conceptual material. I will have a little bit that I'll talk about tomorrow, but it's not going to be as much formal notes. Tomorrow we'll spend more time just working on active and stuff like that in class, and I'll try to give you some more example type problems or example type questions. So today we are still kind of tied into electromagnetic waves, but we're going to be looking at something called atomic spectra. So one of the ways that we can identify elements is by when we burn them, what color light they produce. And we can tell what's in something. So the way that they know what elements are in a star is by looking at that star through a filter, and it produces certain quantum spectra that they can tell it has hydrogen, it has helium, it has some heavy metal in it, it has this in it. Same thing with certain planets. They can look at the light that's reflected off of it and tell what's there. So this is kind of how we use light and reflection to determine what elements are in a substance. So this again goes back and relates to Bohr model a little bit, but it's going to be dealing more with emission and absorption of energy and how the electrons absorb or give off that energy. And then we'll also continue defining the atomic trends. We've already identified atomic radius and ionization energy, but we're going to look at metallic character, electronegativity, and reactivity today. All right, so starting off, the first one that we're going to talk about is electronegativity. All right, so there's actually 2 words that tend to get used here. Electronegativity, and I'm going to write the other one on the board in just a minute. But electronegativity, by definition, is the tendency of an atom to attract more electrons. So based on that definition, which elements do you expect to have the highest electronegativity? The ones that are going to form, let me ask it in this context. Would you expect elements that are going to form cations, positive ions, or anions, negative ions, to be more attractive to negative, the anions? So we're really looking at the non-metals here because they want to gain electrons versus the metals that want to lose. So the other word that they use, so we have electronegativity, and then another the other word that we use is electron affinity. So the difference between electron affinity and electronegativity is basically this, that electron affinity just really says, I want to hang on to the electrons that I already have, versus electronegativity says, I want to gain more. So most of your non-metals, or all of your non-metals, they want to hang on to the electrons they've already got. So they have a certain electron affinity. Some of them want to gain more electrons, so they have a higher electronegativity. All right. So in your periodic table reference packet, this is the one that's nice. It already has the trend in there for you. So if you look in your reference packet, I think it's one of the last pages. but you should have a table that looks something like this, and it says electronegativity at the top. Look at that one and tell me, comparing that to a regular periodic table, aside from the fact that they're only showing 6 rows instead of all 7, what else is missing from that table? Say again? Well, more specific than that, there is something that is just totally not there, and it has to do with the column that helium's in. The noble gases aren't there. So what do we know about noble gases in terms of ions? They don't make ions, right? Because they already have what? They have 8 in their valence shell. They're already full. They're already satisfied. They're not going to bond to make that. So noble gases All right. Noble gases do not have an electronegativity. They have an electron affinity because they want to keep the electrons they have, but they don't have an electronegativity number. So that's why this last column isn't there. All right. So when we look at this, the highest electronegativity is fluorine. The lowest is francium. So that means our general overall trend is increasing to the right. Based off of yesterday's notes, what other periodic trend does that match?
Why do you have a circle and an arrow?
Because I'm showing you the highest and lowest on the periodic table. I was just pointing out 2 elements. So if you look here, this one's reading like a 0.7. Actually, the element below francium, oh, that one does have francium. Francium has like a 0.7 electronegativity. Fluorine has a 4.0. That's the highest versus the lowest. All right. So look back at yesterday's trends. We talked about radius and we talked about ionization energy. Which one does this trend match? Ionization energy. So we're seeing an increase in this direction and an increase in this direction. So the overall trend increases that way. All right. So you can actually, while it's not going to be totally accurate, you can actually use this table to help you remember the trend for ionization energy, electron affinity, and electronegativity. Now, the numbers that are on there only apply to electronegativity, but the overall trend that we see applies to all 3 of them because they all move in the same direction. Just realizing that electronegativity doesn't have the noble gas column. Everything else does. All right. So when we go down a column for electronegativity and electron affinity, when we go down a column, electronegativity and electron affinity decreases. All right. So that's when we go down the column. When we go up the column, it increases. And then as you go across a period from left to right, the electron affinity, the electronegativity increases. The reasoning is the same as before. Remember, as we're going across a period, we're adding protons and electrons. So as you get that higher positive charge, or to use the next level chemistry term, higher Z effective charge, that's talking about the positive charge in the nucleus. As you get that higher charge, that means it it has the ability to pull in more electrons or to grab more electrons and hold on to them. So it has a tighter grip on its electrons. So that's why it increases as we go across the period. As we're going down the column, the reason why it decreases, remember the electrons are getting further and further away from the nucleus because we're adding more and more layers. All right. So, again, I gave y'all the periodic table. The thing that I want you to do is go ahead, cross out that last column because remember, electronegativity doesn't use the noble gases. So over here, I'm going to put fluorine in that box because fluorine is our highest. Francium is our lowest. And so we get this overall increase in this direction. So it increases as we go up. It increases as we go to the right. And these electronegativity. So that last column just doesn't have it. They don't have numbers for it. So, yes.
The bottom row is also called, is that just like this?
So about 6 years ago, I pulled this image off the internet. About 6 years ago, you see the ones that are outlined in white. Those are all man-made elements. So we, at the time that this image, they just hadn't officially named those yet. So that all that is just not showing it complete. That's not a it's there. So OG is technically a noble gas, even though I think in nature, whenever they make it, it's a solid. But we've only ever made it at a couple atoms at a time. Like we don't have mass quantities of it. So now, again, realize these two rows at the bottom are fitting in here. So that trend is still, even here, it's still kind of like up and to the right. All right. Now, so remember that a low ionization energy, if an element has a low ionization energy, what type of ion is it likely to produce? Ionization energy has the ability of how easy is it to steal electrons from it? So it's going to be a positive. So something with a low IE will make a positive ion. If it has a high EN, electronegativity, what type of ion do you think it's going to make? Electronegativity says we want to gain electrons. If I'm gaining electrons which are negatively charged, I heard positive 4 times.
No, that's a negative reverse.
All right, so high electronegativity is going to form a negative ion. So if I look at these two charts together, what element has the lowest ionization energy? Francium. All right. So francium is the most likely element on the periodic table to form a positive ion. What element on the periodic table is most likely to form a negative ion? Fluorine. What would you expect to happen if I put those two in a reaction chamber together? Would it be a quick reaction or would it take forever for it to react?
Quick.
Very quick. Those two are the most reactive elements on the periodic table. So if we put them together, they're going to have a very quick, violent reaction. And it's going to give off a very much exothermic reaction because it's going to give off a lot of heat, a lot of light, a lot of sound. All right. Fortunately, those two are kind of difficult to get by themselves anyway. So I don't have to worry about people trying to do nefarious things with them. All right. So that leads us into reactivity. Reactivity has to do with the tendency of an atom to react. All right. So as I said before, metals tend to lose electrons. And that's based on the fact that metals have lower ionization energy. So they're more likely to form positive ions, cations. All right. So a very low ionization energy means that it's going to be highly reactive. So in the past, I have told you that group 1A Group 1A metals are the most reactive metals. Those are the most likely elements to find bonded in nature that are metals. And then nonmetals tend to gain electrons when they react, and that's based on the fact that they have a high electronegativity and a high electron affinity, meaning they want to hang on to what they have and they want to take on more. So they're going to form negative ions. So high electronegativity also means high reactivity. So if group 1A metals are most likely to form cations, what group off the periodic table do you think is most likely to form anions? 7A, the halogens. All right. So the halogens, group 7A, nonmetals. So group 7A is never going to be found alone in nature. Now, nice thing about nonmetals is, remember, nonmetals can bond ionically. They can also bond covalently. So what else do you notice about group 7A? What's the how do we usually find those elements in nature? Fluorine, chlorine, bromine, iodine. What do those things have in common? They're all diatomic. They're normally bonded to themselves. And that's why, because they're highly, highly reactive. They don't like to be unbonded. And so if they're in an area where it's just themselves, they're going to bond with themselves. But if you take those elements and put them in the area where there's group 1 metals, they're also going to react, and they're going to react very quickly. So think about what's a common substance that we eat that contains or that not necessarily that we eat, but that we put on things that we eat, that contains a group 1 metal and a group 7A nonmetal.
Salt, NaCl.
So table salt, sodium chloride. And that is readily found in the ground. We used to have one of the largest salt mines in the country here in Louisiana that recently shut down because of sinkholes forming. That's near Avery Island in Lafayette, or near Lafayette, Avery Island. Same place they make Tabasco. All right. So, the general trend for reactivity. This one's a little bit different than everything else. So, this column And so looking at this, if we have our metalloid line right there, so what we're looking at is reactivity kind of increases in that direction from the metalloid line, but it also kind of increases in this direction from the metalloid line as well. So reactivity is kind of funky. Those two columns of elements are the most reactive. Everything in the middle, I don't want to say they're non-reactive, but we can dig copper, gold, and silver out of the ground, and it's copper, gold, and silver. We don't necessarily have to find these elements bonded with something. Same thing with carbon. We dig carbon up all the time. Coal, diamonds, all of that. It's just carbon, and it's not necessarily doesn't have to be bonded with something. Silicone, we dig it up. That's basically sand. It doesn't have to be bonded with something. So there's not really a general overall trend for reactivity, just knowing that group 1A and group 7A are highly reactive. Everything else could kind of care less if they're bonded or not, if it makes sense that way. All right. And then the last trend is called metallic character. So one of the things that I want us to... So we can think of elements as metal and non-metal, but we can really think of it more of a spectrum, that if you're way over here, you're more metallic. And if you're way over here, you're less metallic or more like a non-metal. All right. So when we talk about metallic character, what elements show the most characteristics of a metal? So when we think about metals and we look at the properties of metals, one property of a metal is that they're easy to form into shapes. So the term that we use for easily to mold into shapes and form into shapes is that metal is malleable. Basically means that we can take a hammer and we can beat it and bend it into a certain shape. That's the whole idea of blacksmithing is about. All right. And then the other thing that we can do with metal is if we flatten it out into sheets, metals are also ductile, which means we can draw them into wire or tube or piping, things like that. So like we can take a metal sheet, we can wrap it in on itself, or we can fold it in, and we can pull it and draw it out and make other things out of it. All right. Metals also tend to be highly conductive. So metals tend to conduct electricity and heat very well. That's why they have very low specific heats, because they can heat up really quickly and it can cool off really quickly. That's why it's one of the main reasons that motors and engines are made out of certain types of metals, because of their low specific heat. That, yeah, the engine does heat up rather quickly, but it also cools off rather quickly. So you shut it off, that temperature drops pretty quickly. They tend to be shiny. And I think I misspelled shiny, but I'm not going to worry about it. And then when we look at it as a group trend, metallic character, as we go down a column, metallic character increases. So as you're moving down the periodic table, the more like a metal a substance becomes. So I'm actually going to use group 7A to kind of point this out. What do you notice that happens to the phase of matter as we move down this column? It becomes more solid. So we start off as a gas and we become more solid. So as we move across the periodic table this way, notice that pretty much everything is a solid from that point on, with the exception of mercury right there. Mercury is just kind of a fluke. All right. Something about its electron properties and all of that makes it like to be a metal at a liquid at room temperature. But everything else tends to have that solid nature. And that nature of being a solid is one of the things that we associate with metals. All right. They tend to be solids at room temperature. All right. As we move across a period from left to right, metallic character decreases as well. So as I'm moving across from the left side to the right side, again, we can see that trend. So if I'm following across period 5, what you should see is as you get further over, the more likely it is to be a liquid or gas. As we move up, the more likely it is to be a liquid or gas. All right. That's just those general statements. So metallic character increases is this way. All right. So what is the only other periodic trend that has this same direction? First one, which was radius. All right. So to some degree, the character of being like a metal is going to have to do with also how large and how much attraction there is between the electrons and the nucleus, the electrons and the protons. So you become more like a metal if there's less attraction between the protons and electrons, which helps aid in that ability of being conductive, that the electrons can move, carry a charge. It helps with being a solid. It helps with being malleable and ductile versus brittle or gaseous, things like that. There's more to it than that, but that's kind of the gist of what's happening. It all has to do with those arrangement of electrons and the distance of the electrons from the nucleus. All right. So the last couple of things. So we talked a little bit about the Bohr model, but one of the things that we've learned is every element, if we take an element and suspend it as a gas, or if we burn a solid, every element is going to produce certain wavelengths of light when it burns. And so if we look at it through special types of filters, we can see what's called an emission spectrum. An emission spectrum allows us to see, and it's kind of hard to see, and I don't even know if you can see it on your copy because of the way black and white copies. No, you can't. But on here, I have like a little red line right there. I have a blue line right here. I have an indigo line and a purple line right there. So anytime I electrify a sample of hydrogen or burn a sample of hydrogen, and I look at it through a emission filter, a spectrometer, I guess is a spectrometer is what it's called. But if I look at it through a spectrometer, I'm going to see these same 4 wavelengths of light. Every element has its own specific coding there. So when we look at something through this filter, we can tell what element it is basically by this. It's kind of like a fingerprint for an element, or a DNA thing for an element. It's not really DNA and it's not really a fingerprint, but it's a way that we can identify it based off of that. So notice If I'm just looking at pure white light, it has the full spectrum. If I'm looking at hydrogen, I see these certain lines, dot, 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 at those wavelengths. If I'm looking at helium, notice I have similar, but they're not exactly in the same places. So I can distinguish helium from hydrogen. Even if I had both of them in there, I could distinguish that I had both. And then when we get to something like neon, notice neon produces a lot of the spectrum, but not all of it. So that is an emission spectrum. So we're just looking at the light emitted. I'm going to skip a couple of slides, and I'm going to come back to some things. But back up. All right. So now I want to compare the difference between an emission spectrum, which we just saw, versus an absorption spectrum. What do you notice about the emission spectrum and the absorption spectrum on here? It's inverted. It's like the emission spectrum is the negative to that. So if I take this and I slide it up, it's going to fill in the gaps. So an absorption spectrum means if we're looking at something, if we're looking at hydrogen and it's not electrified or something like that, it's going to absorb these specific wavelengths of light. So we could use that again to identify it as well. One way is if we're burning it. The other way is if we're observing it, just as it is in its natural state. All right. They do ask questions about it. So remember, absorption is taking in energy, and emission is giving off. Energy. All right. So we're looking at electrons either gaining energy, that's what we would see with an absorption spectrum, and then the emission spectrum, we're looking at electrons giving off energy. All right. So now backing up, I'm just going to kind of quickly go through this. All right. So when electrons absorb energy, an electron will rise to a higher orbit. So if you remember the little ladder thing that I had, if I give energy to this electron, it gets excited. So it's going to move from here to here. All right, so that's for absorbing energy. So absorbing energy excites the electrons. It puts them in an excited state. When the electrons are in the excited state, it's less stable. It's less stable. So the electron will then, because if it's not stable, it can't hold that position very long. So then it's going to relax down to the lower orbit. So when it relaxes, it releases energy or emits energy. And so it falls from that higher position down to that. When this happens, we see a flash of light or a color of light. All right. And so it does that by releasing energy in a precise amount of quanta. All right. And so light energy emitted by excited atoms consists of specific lines at specific wavelengths corresponding to the specific transition between the two orbits. So as you move and as electrons become excited and then release the energy, they jump to different positions.